welcome tonight. I'm not going to speak very long at all. I did want to say, first of all, that not only do we have free refreshments, we have a policy of no waste on refreshments. Betsy, tell us about it.
So we use cloth napkins, we use reusable plates and cups. So please put your reusable plates and cups in here. We have one for napkins. We compost any of your food waste, so use our bucket here. If you brought anything with you that needs to be recycled, the college provides for that. But let's keep it no waste. Thank you.
And speaking of refreshments, when we did the last presentation at the Montcharm Museum across the river, somebody left this nice travel mug. And if this looks like something that belongs to you, then just stop up and pick it up afterwards. In the meantime, I'd also like to thank the co-sponsors, and indeed, I dare say, it's really nice to welcome, particularly Bob Walker from the Sustainable Energy Resource Group, or SURGE. Many of you know about the work that those guys are doing, particularly their efforts in organizing municipal community energy committees that have been so active in this area in making a difference. But also the League of Women Voters, and indeed if you like the refreshments, you can thank in part the League of Women Voters. And if you probably become aware, as I have recently, that you don't have to be a member of the female sex to be a member of the League of Women Voters. And indeed they do an awful lot with elections coming up. They are going to be, again, a prominent player in that game. The Transition Town, the 350.org, Bill Wiggin and Company, the Norwich Energy Committee, one of the groups that has been so active. Hanover Conservancy, the Catamount Earth Institute, thanks for their co-promotion on the co-sponsorship on it. Hanover High School Environmental Club. Anybody, any students here yet from Hanover High School? Yes. Hey, one of the things one of the preceding things that we did was with Rob Hogg, who's a state senator from Iowa, and he gave us a whole bunch of books, very good on describing climate change and what it's all about. And what you should do is take not only one, but take them all back to the club members. And Jeannie Kornfeld, yes, who's very active and wants to, and can distribute them to the other members of the environmental club. But it's a very readable. The Cornish Energy Committee is even here, and Sustainable Energy. Yeah, but you know, appreciate all the co-sponsorships. And one of the things that a misapprehension that sometimes occurs is that those in environmental groups are at loggerheads, or they're all competing for your donation dollars. But this shows that, hey, that's not exactly true. We work together, and whether you're donating funds to SURGE or the League of Women Voters or the Sierra Club, your money is being well used, yeah? And we're not so much in competition, but as this shows tonight, collaborating for common goals. Our next co-sponsored event will be December 3rd, again at the Montcharm. It'll be Andy Friedman, Professor Andrew Friedman of Dartmouth's Environmental Studies program, who's talking about biomass, and particularly burning wood. And he's done a lot of research on this. And he asked the question, should I burn wood, and how much should I burn? Is it all right at a personal scale? What about all the way up to the industrial scale of burning wood to generate electricity? It's going to be fascinating again, December the 3rd, 6:30 p.m. at the Montcharm Museum. Tonight's agenda, again, with Frank and Jonathan. He's just going to speak for about 15 minutes, but we wanted this to be as Socratic as possible and get as much audience participation as we can. So they're each going to speak for about 15 minutes, and then we will open the floor up to questions and comments from the audience. I'm not going to tell you about where they went to kindergarten and list all of the reports they've published over the years. Just to say that Frank did his graduate work at the University of Wisconsin. I did my undergraduate work at Purdue, so we're arch rivals with Wisconsin. And Frank did his graduate work at MIT. And I got
Jonathan.
My graduate work, and what?
Jonathan did it at MIT.
Jonathan, right, at MIT. And my graduate work was at Caltech, which is an arch rival at MIT. So I knew he didn't like these two guys from the start, but still we invited them because they're very knowledgeable. Frank particularly on stream channel and watershed response to environmental change. And be that environmental change something that's man-made or something that's natural. Indeed, you may have seen him recently in the film The Last Irene. He was featured in that. His research is particularly looking at the causes of major storms and disasters. Jonathan's work has been particularly on the impacts of climate change on agriculture and water resources. And indeed, I'm going to stop right there because I want to hear what these guys are going to say. Again, Frank McGilligan and Jonathan Winter, both of them. Give them a hand.
Thanks. So I'm going to go ahead and start off the presentation. As Dennis mentioned, please feel free to interject with questions. We want to keep it informal, a nice discussion. So what I'm going to discuss is I'm going to start with a quick introduction to the Intergovernmental Panel on Climate Change Fifth Assessment Report, which just came out. I'm going to give you a little background on global climate models and how we try to use them to look at climate change impacts. And then finally, I'm going to go into some projections that we've done over the Lake Champlain Basin and basically how we see that impacting that region. So to motivate this discussion, I pulled down a few pictures from the internet. The first one being a farm stand in Vermont. And if you notice, it was a little bit harder to find a pumpkin this year. You were right, because there was a significant decrease in the harvest, partly due to a very wet spring in the Northeast. It's a niche example, but agriculture in New Hampshire and Vermont combined for about $1 billion of value of output per year. Another important industry in the Northeast is the ski industry. This is a picture from Stowe, Vermont. And it's a snow gun, and it was an article describing a $4.7 million investment in snowmaking equipment. Also a very climate-sensitive industry. And finally, the poster child for climate impacts on the Northeast. This is the outflow of the Connecticut River post-Hurricane Irene into the Long Island Sound. It's a satellite picture. Obviously, Irene had devastating consequences for this region. So, I'm going to start with the Intergovernmental Panel on Climate Change. This is a big multi-institutional panel that puts out every, I believe it's 4 years, a report on the state of global climate change. This year, it was released about a month ago, and the main headline was that scientists are now confident, and confident being 95 to 100% confident, that global warming is caused by humans. This is what the report looks like. This is part one of the report. This is the physical science basis, so this talks about the projections. Part two has already been leaked, but officially comes out in March. That's on impacts. Part three is on adaptation. That comes out in April. And then finally, there's a synthesis report that comes out in July that wraps everything up. So I went through the report, and I pulled out an interesting figure that I thought was a good motivator that shows the relationship between carbon dioxide and temperature. And this is what I came up with. So this is from the Fifth Assessment Report. So you have cumulative total anthropogenic CO2 emissions, so the amount of CO2 we've emitted since 1870. And on the y-axis, you have a temperature anomaly relative to some pre-industrial time period. And over the observed period, which is this black line with dots in through here, you can see that nice relationship that we all recognize between CO2 and temperature. This black line charts a 1% increase in CO2 per year. And then of more interest, these are the new representative concentration pathways. So these are the different emission scenarios that the IPCC now uses when they're looking to project future climate. So they range from 2.6, so the way they're denoted is by their radiative forcing at the end of the century in watts per meter squared. I know that's a mouthful. But they range from 2.6 to 8.5, with 2.6 being a less emissions-intensive future, and 8.5 being the most emissions-intensive future. So you can see that. So if you look at the red, which is 8.5, you have something like 2,000 gigatons and 4.5 degrees of global mean average temperature increase. The swath that's traced through here, that's basically our uncertainty. So that's the spread of the GCM, some measure of the spread of the global climate models that we use to project temperature forward, and their different responses to basically CO2 emissions. So besides that quick motivating figure, I'm not going to do any more discussion of CO2 and the relationship to climate change and the physics of climate change. If you have questions, I suggest you go view this excellent talk given by Brad Marson. He walks through a nice radiative argument for both historical climate and climate under CO2 emissions. What I am going to talk about is general circulation models. So these are the models we use to project future climate, and they solve a series of physical equations, and they predict fluid flow or climate on a spherical surface. So we start them in some arbitrary time, 1900, and run them to 2100, and at the end, we have a projection of future climate that is, we hope, accurate. They come in different flavors. They can be atmospheric only, so they have a prescribed surface, or they can be oceanic, so they have a prescribed atmosphere. Or they can be coupled atmospheric, oceanic, general circulation models. And when you hear people talk about just the general circulation model, global climate model, GCM, that's what they're talking about, these coupled atmospheric, oceanic, general circulation models. And that's what I'm going to be talking about for the rest of this presentation. They're nice because they're global and spatial coverage, but their drawbacks are they contain significant inaccuracies, so we're not perfect at predicting climate. And also they have a coarse resolution. So to illustrate that, what I did is I took a picture from NASA's Terra satellite, and I put it at full resolution on your left. That's 5400 by 2700 pixels, and I put it at GCM resolution on the right. So basically I aggregated the pixels so it's only 360 by 180 pixels on the right. So that's 1 degree by 1 degree is a pretty common resolution for a GCM. This is in no way scientific, but just gives you some idea of the kind of detail that you lose when you go from the full representation of the Earth to this 1 degree by 1 degree representation of the Earth. So if you break open a GCM, what you find inside of it is basically all the things you find in a global climate system. So you have your atmospheric radiation, basically the eccentricity of the Earth, the solar constant, the tilt of the Earth, tells you how much is hitting the top of the atmosphere. You have your resolvable scale clouds of precipitation. These are your large scale frontal patterns that come through and give you drizzly rain. You have convective clouds and precipitation, your pop-up thunderstorms in the summer. You have a planetary boundary layer that gives you the exchange of water and heat between the surface and atmosphere. And then depending on the flavor, you either have an ocean model or some kind of prescribed sea surface temperatures that are giving you your ocean fluxes. And then, of course, you have land, your surface physics, so that's everything that you experience every day. The vegetation beneath your feet, soil moisture, the long-wave radiation out from the surface, basically the entire surface. So I mentioned that a couple drawbacks of GCMs are first, they contain inaccuracies, and second, that they're coarse spatial resolution. So what we do to address this is we statistically downscale them, or one of the methods to address this is statistical downscaling. So the basic idea behind it is we're bias correcting and downscaling based on historical climate data. So to do this, you need good, high quality, high resolution observed data. And an easy way to think of this, and it's more sophisticated than this, but say Hanover and Mount Washington are in the same GCM grid box, which is completely possible. We know on average the top of Mount Washington is going to be colder than Hanover. So we know that from the observed data, so we can basically downscale the data. We can say, okay, over Mount Washington, make it a little bit colder, Hanover's warmer. That's downscaling. And say that any given GCM has a historical projection that's 2 degrees too warm. You know, it's an error, it's a bias. Well, we can say, if on average it's 2 degrees too warm, just take away that 2 degrees. We know it doesn't belong there because we looked at the observed record and it's not there. So that's the basic idea. Again, it's more sophisticated, but you're mining information from the observed data to correct your GCMs. There's multiple ways to do this. But what it does do is it gives us these nice high-resolution data sets. Yeah?
What's a typical time resolution, time step, if you're advancing dynamic recurrence?
GCM?
Yeah.
An excellent question. I work with regional climate models. It's on the order of seconds, but you would never trust data down to that. You trust data maybe aggregated up to days over long time periods, and mostly you're working with monthly data. That's what you're most confident in.
So,
But on the model is actually kicking through, every, it's time evolving over minutes or seconds. So it runs every minute of, 1900 through 2100. So they become very high resolution. So you can go down as high resolution as your observational data set. So here I'm talking about an eighth of a degree, which is about 12 kilometers. But of course, they're limited in spatial coverage because you have to have this high quality, high resolution observed data sets. And then also they remove some of the accuracies in GCMs. One of the other drawbacks, and this is a little bit subtle, but because you're using observations, some of your ability to freely predict the future is removed. So that's that last line. So you basically go from this 360 by 180 pixel representation of the world, and you claw back some of that resolution. So this image is basically an eighth of a degree, so 2880 pixels by 1440. So what does this look like over the Northeast? So I coarsened our GCM a little bit. This is a 2.5 degree GCM. But you can see the standard grid box is basically bigger than the state of New Hampshire. And so what we do is we go through and we statistically downscale to get down to 12 kilometers. This is a picture of temperature. This is an image of temperature. So warm colors are warm and cold colors are cold. And you see some of the features pop out. Like now we have a coastline, and we have the White Mountains and maybe the Green Mountains in through here, and maybe the Adirondacks. But the idea is that we claw back some of this information that gives us a better idea of local scale impact. So the results that I'm going to be showing are for the Lake Champlain Basin. This is work that I did with Justin Gilbert and Brian Beckett at the University of Vermont. And we were basically looking over this domain. So all the figures I'm going to show from now on are averaged over this domain. These are your eighth of a degree grid cells. And for references, here is where you are right now. Okay, so before I get into the projections, what I like to do is first look at the historical trend. So it's nice to see what the models predict, but it's also nice to look back and see what's happened in the past 50 years. So if you look first at temperature, pay attention only to the red line. The blue line's for Burlington, so we're not going to bother with that. We just want to look at an area average. So this is temperature, and it's been increasing steadily. And if you work out that trend, it's about 0.2 degrees centigrade per decade. So about 1 degree centigrade since the 1960s. So climate is warming. And then if you look at precipitation, you can see the trend is also increasing. This is to the tune of about 0.12 millimeters per day per decade. So this is not the case in all regions of the U.S., but the Northeast just happens to be an area that's getting wetter, and there's a large literature that supports this. So basically, climate is getting warmer, climate is getting wetter for us. Okay, so now we're going to look at the projections. Don't be scared. Look at the top panel first. We're going to ignore the bottom panel completely in the interest of time. So in the top panel, what you're seeing is basically the change in temperature from the future projections minus the historical. And the historical period being 1970 through 2099. So this is mid-century minus historical, end of century minus historical in red. And you're looking at the difference in the temperature. So this gives you it by month. This gives you the annual average. The filled in circle, that's the mean. Okay? All the other symbols up and down, those are some range of uncertainty. I'm not going to go into exactly how we did it, but these are different GCMs, and these are different RCPs. So different models, different emission scenarios. Yeah.
Say just a word about what kind of boundary conditions you need, whatever, before you get those boundaries.
Well, so it's a global model, so there are no boundary conditions. It runs the globe. Does that make sense? So there are initial conditions.
I had the idea you were doing something finer resolution inside the region you marked.
Yeah,
Before you get
so-
to the boundary conditions.
Right, so you basically...
Repeat the question.
Oh, I'm sorry. So the question was, what are you using as your boundary conditions? So it's not actually that we're running another model in that area. That would require boundary conditions. But all we're doing is taking those big cells and using high-resolution observed data sets to downscale it. So I'm just, there are no real boundary conditions. It's just taking some of the cells out of the GCM and downscaling them.
You're not doing anything dynamically that's fancier inside the perimeter
Nope.
area.
Nothing that's fancier. It's basically just using, it's a statistical process that doesn't do anything fancy around the inside. It just uses observed data. So boundary conditions are for regional climate models, which I also use. And there you do need boundary conditions and they become very important. But for here, we're just using the full GCM projection and we're picking out different grid boxes from the GCM and downscaling them. So as you can see, we have projections of warmer temperatures, somewhere in the range of, and this is a big range, and we chose these GCMs and RCPs to expand the range, so we wanted to look at the full range of uncertainty. So somewhere between 8 and 2.5 degrees centigrade, which is a big range, but on average, you have maybe 4 to 4.5 degrees centigrade by the end of the century. So, and all models agree on the warming. And one thing to note is that you'll see more warming in the winter, and that's a result of decreasing snowpack. So once you clear out that snowpack, you get a much higher albedo or a much lower albedo surface, so you get a much darker surface that absorbs more sunlight. So let's look at precipitation. So precipitation is a little bit more nuanced. So you see on average, it does pop out that we get wetter by mid and end century. So annually average, it's wetter. But we do see some more detail in the seasonal cycle. Not every month is wetter. You can have range from 20% increase precipitation to 20% decrease, depending on which GCM and which basically emission scenario you want to believe. Overall in winter, you generally see a wetting trend, which is kind of logical because you're going to have warmer air which can hold more moisture, and you're going to see more of that moisture as rainfall instead of snow. So overall, the seasonal picture is a little bit blurred, but you still get wetting by the end of the century, by mid and end century. Okay, so now what I'm going to do is I'm going to take those temperature and precipitation projections, and I'm going to show you some kind of impacts through climate metrics. So the first one we're going to look at is days over 90 degrees Fahrenheit. So this, unlike all the other figures, is for Burlington only. Because if you average that whole area, it's actually pretty high in altitude, so you don't get many days over 90 degrees Fahrenheit. So this is for Burlington only. You can see that heat waves are not a huge problem in Burlington at the moment. They get about, on average, at their peak season, about 3 days above 90. But as you move into the future, you see almost a six-fold increase in July, and that has implications for basically cooling requirements. We'll have to get air conditioners in hospitals and community centers for vulnerable populations. It has implications for air quality because smog formation is basically a function of heat and sunlight. Days over 90 significantly increasing. Growing season length also increases. So the growing season length here we're defining as basically the longest time period between two freezing days. So it's not a really sophisticated agricultural definition. It's more of a, is it warm enough that we could potentially grow crops? Right now we're at about 140 days. We can tack on anywhere between 30, 35, 40 days, and then by the end of the century, depending on which GCM, again, in which scenario you believe you're tacking on closer to 30 to 50 days. And you know, in theory, there's potential that we have a longer growing season. Maybe you could do something interesting with that. But there's also concerns that there's more variability in the spring, so you put your crop in when it starts to get warm, and then you get a freeze that kills it. Or you plant during the original growing season, so what we have right now, but then it gets too hot during the summer, you know, so you have to plant a more drought-resistant or heat-tolerant varietal. The growing season lengthens, but there are issues in using a lengthened growing season and some issues with variability that are still kind of outstanding. So this is probably the greatest stretch of our temperature and precipitation data. So we tried to do days of maple syrup production. So we talked with an expert at the University of Vermont. He said if you have a minimum temperature below 30 degrees, a maximum temperature above 36 degrees on the same day, that's a good day for maple syrup production. So we did a run at it. So here's the current production. You can ignore the left-hand plot. That's the century, but let's just take end of century. So you can see this double peak. So basically, you can get sap in the spring and the fall. And what you really transition to by the end of the century is this more or less single peak, basically at the very end of winter. And if you integrate under these curves, so you look at the total number of days that you can potentially tap trees, it goes down by 11 days by the end of the century. So this is actually this is maybe not the most sophisticated analysis, but it's an interesting result and something that's cool to look at. So the last slide I have is on monthly derived snowfall. So for any of the skiers or snowboarders in the room, so basically by the end of the century, you see a 50% decrease in snowfall, and you lose some of your shoulder seasons, especially. So, you know, increasing temperatures, it's not that this water is going away, it's just that it's falling as rain instead of snow. And with that, I'm going to hand it over to Frank for a more in-depth discussion on floods. Close the PowerPoint for you.
I want to pick up a little bit where Jonathan left off, but also by way of introduction. I'm Frank Gilligan. I'm in the geography department, as Dennis said, and my specialty is fluvial geomorphology. It's always great you say that at a cocktail party. Hi, Frank, fluvial geomorphologist. People just walk away like you say serial killer or something like that. So I am a card-carrying fluvial geomorphologist. And I've been working on floods for the past 25 years or so. I did a lot of work in 1993 Mississippi River flood in the upper Midwest. I worked on glacial outburst floods in Iceland. I've been working as well on a lot of floods here in New England since I arrived here in 1990. So I just wanted to just pick up where Jonathan left off. Jonathan was focusing more on sort of climate change and agriculture. In particular, I want to do is look at some of the sort of regional scale analyses as well in terms of issues of water supply, but also floods as well. So I want to start off and just briefly just talk about sort of the regional hydroclimatology typical of New England. And one of the things about New England from a climatological and hydrologic perspective is it's an incredibly robust area for flood production. If your business is floods, this is a great place to be. We have various types of floods that's completely leafed out yet. You have these high intensity storms falling on the landscape, generally associated with some of our major sediment producing storms, which has tremendous impacts on the water quality as well. So again, basically then during the summertime, we see in part because of the tremendous demand for evapotranspiration for plants and for crops, we pull that water down. Essentially our low flows are occurring sometime around August to early September, and then as we're experiencing certainly for this fall, there's also then a series of precipitation begins to occur again. Evaporatranspiration losses are declining, and stream flow, the base flow is going up as well as the peak. So we can look at this then in terms of sort of what these the lower flows are like, as well as what the peak flows are like for a place like typical river, typical year in New England. But also when I went through the record and I tried to pick out then the largest flood of the year, the annual flood, and plotted that against time, again for the White River at West Hartford. Plotted on here as well is stream flow in cubic feet per second. And the White River at West Hartford has daily data going back to 1916. It's one of the oldest USGS stream gauges in the United States. It's unregulated, and there are no dams on the White River, so it's a tremendous case study to look at, impacted primarily by the land use change or climate change on stream flow. So we look at this one just when I started grad school, the 1936 rain on snow event. Again, a regional, tremendously large flood as well. Another one here at 1938 hurricane. And basically, we see on average about 20,000 CFS, cubic feet per second, on the sort of annual flood series. Again, now we look at these sort of hurricanes, and now we sort of completely change our scale, and we go to some of the real two major floods throughout the region, throughout New England, or maybe not throughout all of New England, but certainly one of the real bell ringers here on the White River was the 1927 flood in November 3rd through November 5th. So really the tail end of the hurricane season, 127,000 cubic feet per second on the White River. This is quite an unusual storm. It was a tropical storm, and it came up along the coast, went straight up the White River Valley, stalled over the Green Mountains, went back out to sea, picked up some energy again, and came right back up the White Mountains again, Green Mountains into central Vermont. So getting on the order of about 30 inches of precipitation in a 4-day period. So basically about 80% of the annual precipitation occurred in the upper White River. Also, it's the low evapotranspiration time of the year and not much vegetation out, so it really led to a significant flood. So the 27th flood for many portions of Vermont in particular is the flood of record. The whole series of towns here, there's Winooski and a bunch of other towns. I think that's the White River crossing through there. So again, it was the real bell ringer of a flood. And we have other gauges as well that go across New England. It's one of the densest areas of USGS stream gauges, but not all of them go back to the 1916. Most of them begin to come in after the flood of 1927. In context then, also something I'll come back to at the end of the talk later, is trying to capture then what occurred with Hurricane Irene. And so for some portions of New England, I'll show some slides of this in a second, it was the flood of record. Hard to tell how it would have compared to places that got hit by the 27 flood, but also the 27 flood was much more sort of regionally specific, not as widespread throughout Massachusetts and Vermont as with Hurricane Irene. And New Hampshire kind of got spared a little bit with Irene. Basically, the eye of the storm came up the Connecticut River Valley. Basically, then, generally what we see with precipitation with hurricanes anyway are intense low pressure cells like that. It's the western portion of the low pressure cell that gets most of the precipitation. But this is exacerbated by the orographic uplift coming up the spine of the Green Mountains. So basically, the tracking of Hurricane Irene paralleled the strike of the Green Mountains and basically had tremendous amounts of uplift coinciding with the normal wet side of the hurricane, which is what we normally see. Basically, it led to quite a tremendous economic cost to the state of Vermont. Basically, the number of roads that were wiped out, bridges that are wiped out. I'll talk a little bit about culverts as well. And essentially, the state is still, in many ways, Hurricane Irene may have happened in August, but for many parts of the state of Vermont, it's still going on. Right? People are still trying to recover from Hurricane Irene. So one of the things we want to talk about is sort of what's going on in New England, or what has been going on in New England over the past several decades. And Jonathan alluded to as well a lot of these climate models, but in terms of downscaling, ways we incorporate observational data to go along with some of our modeling data. There is this sort of this tension sometimes between models and empirical data. Some people sort of deny the role of models in part because they're based on assumptions or they're simulations, and a lot of people, in fact, like good old hard evidence, so the empirical evidence that sort of proves a particular point. So I want to focus on, Jonathan talked mainly about some of the models and the GCM projections for what's going on in New England, and I want to talk a little bit more about what has already been observed occurring, occurring in New England over the past 5 or 6 decades or so. Right? So we look at this then in terms of what has been going on in New England. Again, as I mentioned, there's been a tremendous effort by the U.S. Geological Survey, mainly out of Maine. And they've been publishing a whole bunch of papers trying to capture these kinds of changes that have been occurring over the past 5 or 6 decades or so. Most of this work by Glenn Hodgkins, but also by Thomas Huntington. And here's looking at those hydrologic parameters, again, that Jonathan was alluding to, looking at changes in precipitation. How is that manifesting at the regional and watershed scale? And in particular then, how is this occurring in terms of low flow conditions? Also, what's going on at the other end, so trying to capture those end members between some of these base flow conditions and these larger flows. But also, one of the things also that Jonathan alluded to is that there have been significant changes in precipitation, in particular, how much of the total precip for New England is now falling as snow. This is one of the major changes that have been going on. Jonathan mentioned in terms of snowmaking. This requires a tremendous amount of more funds to generate the kind of snow that you all need to go skiing in. But also, from an ecological perspective, not only do we have to worry about what's going on in terms of the magnitude of these flows, but also the shifting timing and seasonality as well that goes along with it. Fish and other benthic macroinvertebrates and other critters living in the rivers have expected a certain timing of either minimum flows or peak flows for things like spawning cues, predator-prey relationships. So shifts not only in magnitude matter, but from an ecological standpoint, it's also shifts in the timing of these flows, the low flows or high flows, but also have a tremendous impact on the aquatic or riparian ecology. So this is some of the work that Hodgkins and Huntington have been doing throughout New England. And again, one of the things that they're sort of showing, again, that Jonathan alluded to, is that if we just assume not much change in precipitation, but it'll show, as Jonathan did, that precip has basically been increasing throughout New England and parts of New York. But basically, one of the things that we see in this analysis is that basically what we're looking at is that there is a smaller proportion of the total annual precipitation that's occurring as snowfall. And not in every gauging station, but in most of the gauging stations, the climate stations that we have in New England, scattered from Vermont and in fact extending into New York as well, across to Maine, that basically much less of that total precip is occurring as snow. So when your grandfather tells you we had to walk uphill both ways and snows up to his shoulders, he was probably right. Okay, there was more snow back then. Of course, whoever he told you he went uphill both ways, he probably wasn't truthful about that topographically. So here, just looking at some statistical expressions of this, what's known as lowest regression of lowest curve. We see that over time, again, what we're seeing is that less of that snow is occurring in December, and less of that is occurring in April. So we basically shortened that snow season, right? We've curtailed it at December, we've curtailed it in April as well. What they found for their analysis, without getting too lost in their study, but basically their time series supports a decreasing trend in annual and winter snow to precipitation ratios over this 60-year period. So this is a measurable change that's occurred at the regional scale in terms of snowfall. And that these patterns in the annual and winter decrease in snow to precipitation ratio are similar to and consistent with, this key thing here, with other hydroclimatological analyses, things and changes in base flow, changes in instantaneous peak flows, and basically a preponderance of evidence is one of the things I want to try to present to you in the next several minutes or so. One of the things they also looked at, which is also critical for me as a hydrologist, is that it's not just the big flows that matters, it's also the low flows that matter as well, both in terms of ecological conditions, but other geomorphic conditions occurring in the stream. So basically, in August, what we see is that these are the base flow, or basically the low flows throughout the summertime. Basically, we see for most of our basins, excluding northern and or coastal Maine, that basically what we're seeing is a tremendous increase in low flow conditions over time. We can also represent this in another mean. This is the 7-day low flow base flow. So basically, what is the average of the lowest 7 days in a given year and how that's changed over time. And basically what we see again from Connecticut, through Massachusetts, up across into Vermont and New Hampshire, that basically our low flows are getting larger. Our base flow conditions are getting larger. And certainly one of the things that's driving the bust in terms of this hydrologic relationship, of course, is going to be increases in precipitation. Right? So we look at this in terms of summer precipitation over the past 60 years or so. But basically, again, the size of these triangles denotes the percent increase associated with these precipitation changes.
This total precipitation we're talking about?
I think it's total precipitation. Okay, for this. Right? So again, what we see here is that summer precip increasing over the past 50 or 60 years. And again, in terms of the summer storm flow, so what are these larger flows as well occurring during summertime? But basically, what we're seeing is that low flows are increasing at the summer scale over time, as well as the larger flows as well. Some work by Matt Collins at NOAA in Massachusetts is also looking at changes in the largest flow per year for these various gauges measured by the U.S. Geological Survey. And again, the size of the triangle giving you some idea of the relative increase. So we're seeing basically tremendous increases at both end members of stream flow. Low flow conditions are increasing, and instantaneous peak discharges are also increasing. Again, this is observed data, measured empirical data. This isn't based on any modeling. The other thing that the main USGS people have been doing is looking at ice out dates. Right? So this again is another indicator of changes in temperature. And one of the things that they see, again, over this long time period going back about 100 years for some instances in some locations, or certainly what I have here going back 150 years or so ago. And basically what we're seeing is that all those lakes that freeze across through Maine and parts of New England, that those ice out dates are occurring progressively earlier in the springtime. So one thing that's also changing, we'll see in a second, is that not only is ice out dates occurring earlier, but also the timing of that spring freshet is also decreasing. It's becoming progressively earlier over time. So we're changing, again, very much probably has a lot to do with the amount of snowfall, as Jonathan was talking about. But basically, those spring freshet floods are occurring at a much earlier time, and ice out dates are occurring also at a much earlier time. All right. We shift gears a little bit and start thinking about, again, at the macro scale, some of these various hydroclimatological mechanisms. Certainly the one we're all sort of familiar with, it's on everyone's mind. Certainly what happened with Hurricane Irene in 2011. By the time, at one point it was a Category 5 hurricane, then when it made landfall, it was degraded to a Category 3. By the time it arrived in New England, it was downgraded again to merely a tropical storm. So one of the vexing questions we have in terms of trying to relate some of these various mechanisms, especially things like hurricanes, or what are the long-term observed trends, but also what are the projected trends into the future for these hurricanes. And here's just some work for the Atlantic Basin solely. Basically, again, one of the things we see either for all hurricanes, shown here in blue, or these major hurricanes, which are Category 3 or 5, that is basically there's some variability. And again, there's a tremendous amount of effort by NOAA and a host of other scientific communities trying to unravel what's been going on in terms of hurricanes, or in the Pacific, it would be called a typhoon. It's certainly one of the things that just occurred in the Philippines. It's generated a lot of questions about climate change and the intensification of these storms. So again, this is mainly for the Atlantic Basin, and things seem to be quite variable, certainly not really intensifying in frequency over time. There's a great paper that came out in Science about 8 years or so by Webster and some of his colleagues. One of the things they tried to do is to unpack the global record of hurricanes. And one of the things that they're showing from the going over this 50 or 60 year period is that the number of hurricanes hasn't necessarily increased over time. But one of the things that we see is that essentially the frequency of Category 4 and 5 hurricanes hurricanes has increased over time. So the lower hurricanes have become, and most of this has been in the Indian, coming up the Indian Ocean or the Pacific area, but basically not much trend in these smaller hurricanes, but again, consistent with perhaps a warming ocean, is that what we see is that there's a greater intensification of these much larger Category 4 and Category 5 hurricanes. And then whether or not they make landfall, that's something else. Right? But in particular, one that did make landfall was Hurricane Irene. Again, basically what we see here, just the path and trajectory cutting across the western side of the Berkshires, basically just going up the Connecticut River valley. So the eye of the storm came up the Connecticut Valley, and so most of us in New Hampshire, other than the Pemigewasset Basin, were pretty much spared the impacts of Irene. It was not the flood of record, hardly at all for any of these gauges. For the Pemi, it was a pretty large flood, but still paled in comparison to some of these floods in 36 and 38. So the western side of these hurricanes tend to get most of the precip anyway, but also the spine of the Green Mountains also lending to that topographic uplift, which led to totals upwards of about 10 or so inches of precip occurring in less than 24 hours. Another thing was high storm totals associated with Irene, but also of a really short duration event. And it's one of the things that's really critical in terms of generating these large floods, and had been preceded by a relatively wet 2-week period in mid to late August or so. So we look at the stream flow, and this is a basin that I've been working in down in southern Vermont, Saxons River, near the town of Saxons River. Here again, looking at our hydrograph coming across about August 22nd to August 29th. So basically it goes from about 30 cubic feet per second up to 12,000 cubic feet per second, and it does this in less than 16 hours. Okay, so this gives you some idea of the intensity of the storm manifesting geomorphologically, but also hydrologically. You don't find, generally we don't have those really short duration storms. That's more typical of the American Southwest. We have those flash floods. So basically the peak of that storm, the time to peak was on the order of about 12 to 16 hours, depending upon where you were in Vermont. And again, there were tremendous geomorphic, but also social impacts as well associated with Hurricane Irene. Again, I'll show a picture of this bridge coming out. I think something like 12 or 15 covered bridges came out across New England, but only about maybe 5 or 6 of those were historical covered bridges. A bunch of them were historical bridges built in 1958 or something like that, made to look iconic and old. But really, we lost about 5 or 6 of these mid-1800s covered bridges throughout New England. You see there's one there. I don't have to remind you, this is one I think coming off Simon Pierce there. Again, sort of tremendous amounts of, one of the things from, as a geomorphologist, what we also saw was not only large, as you can imagine, peak discharges, but enormous amounts of bank erosion and hill slope failure. And this is very unusual for places like New England to have this level of mass wasting and hill slope erosion associated with these large floods. The other thing that's also quite striking, go back to the sediment here, is how turbid the water was. And again, this had a lot to do with this rapid rise rate associated with Irene, and then high intensity precipitation coupled with the tremendous amounts of hill slope and stream bank erosion. So this is some data that NOAA has compiled for Vermont. And there's a series of basins, Mad River, Otter Creek, the Dog River, and the Winooski River up in Montpelier. And basically, again, the shape of the hydrograph, in this case, rather than discharge, looking at in terms of the elevation of the water plotted against time. Essentially, one of the things we see is basically we go from base flow conditions to peak flow, in this case, in less than 12 hours, about 9 hours to reach the largest measured flow in a 60 to 70 year record. Again, especially for something like the Winooski River, that basically it crested above the previously high recorded peak discharge, and did so in most basins in New Hampshire and Vermont, primarily Vermont, generally on the order of about 14 to 16 hours, which is an incredible rise rate associated with the kind of geomorphic impact. But again, one of the ones that also has been on everyone's mind, certainly living in Lebanon, some of the events, the microbursts that have occurred this summer. This is the one, these flash floods that occurred in the early part of July, basically hammered the city for the second straight day. Basically Bank Street, but also one of the key ones was Slayton Hill Road redevelopment project by Rivermere. This was, I think they had just finished construction on this, maybe a week before, or something like that. Essentially, this people had just moved in, and a week later, basically, this is what the exterior of their houses look like. One of the things that happened with this microburst, if you will, we had relatively wet period. June was an incredibly wet month, for those of you who were here. June was quite wet, and this storm was on the order of a couple of inches in less than an hour, if not. In fact, the one in August broke the record in Lebanon for the most intense storm in the shortest period of time. So what ended up happening is that the water could barely get out of the hill slopes and into the river channels. And so one of the things that I've been wrestling with is trying to come up with a definition for a flood. Generally, in my field, when we think of floods, it's essentially then the river no longer has the capacity to handle the water being delivered to it from the broader watershed. What we saw instead here for these storms in Lebanon is that essentially what we had was localized areas got dwarfed by the amount of precipitation combined with failing infrastructure. And this is a huge issue that we're all trying to grapple with here. And essentially we saw that for Slayton Hill Road, the water couldn't get out of the hill slopes and get down through the culverts and get down into the channel, basically then probably not generating the kind of flooding that was too short of a storm to really generate a regional scale flood. And basically these culverts, but also the side of the road, basically became the new stream channel. Right? So it had where they dug out perhaps a little bit of a gully there for some evacuation of water. The water got diverted and came down there. The water, the fastest way down slope was not over the river, over the highway to the river. It was parallel to the strike of the highway system. Tremendous amounts of infrastructure here. So this anatomy of a flood, certainly one of the things that occurred was a failure of a concrete box culvert, but essentially the water could no longer get underneath and get into the Mascoma River, and basically the pathway of water was road parallel. Right? So this was an intense storm, couldn't get out, getting into the culverts. So in all these instances for these floods that we found for Slayton Hill, that it was primarily failed infrastructure associated with this. Right? A couple of last slides. This is some work also by Matt Collins and some of his students from NOAA. And one of the things that they've been plotting as well, besides trying to capture the size of the largest flood of the year, or the largest flow of the year, and how that's changed over time, is to try to express it more in terms of average conditions. So what is sort of the average flow and how that's changed over time. And one of the things that we see is that also, like we saw, the preponderance of evidence, those large peak floods were increasing regionally over time. You see this as well for these smaller flows as well. Where does this come up to? What are culverts designed for? Right? Culverts are designed for these more average scale flows, right? Something in the order, not the 100-year flood per se, but something generally in the order of about a 2-year flood, or at most probably about a 10-year flood or so. And essentially what we have a boatload of culverts in New England. And some work that I did with Nature Conservancy several years ago, that basically we enlisted the support of various watershed groups and councils, a bunch of volunteers, and they covered the entire 1,100 square kilometer Ashwelot Basin, and every time they came across a road stream crossing, they had to come up with an inventory of the quality of that infrastructure. Right? That's not me. Right? So as part of that is how big is the culvert, and from an ecological standpoint, what we're really concerned with, and YTMC was involved with it, is basically the upstream portion of this river might as well be on the moon, because the fish can't get to it, right? Not even salmon can get up there. But basically what we measured, and they measured, was the not only the size of culverts, the conditions of the culvert, whether or not that culvert was associated with what was the elevation of that lip between the base of the culvert and the river. And essentially that's describing whether or not it's a fish barrier or not. So as they did, these various watershed groups did it, and primarily tried to look at it in terms of hazard classification. That basically on the horizon we have a big issue with infrastructure in New England. A lot of this is real aging infrastructure. The culverts aren't large enough to handle the increased size of even the average flood. We're not even talking the 100-year flood or 500-year flood here, but most of our culverts are under-designed to handle something in the scale of a 2 to 10-year flood. And it's just some work I did this summer on a panel evaluating New York City's climate change scenario. And basically, New York City is being quite proactive here. and trying to come up with a plan, a water supply plan for New York City. It's the largest industrial area in the United States that does not filter its water. Okay? So the only way you can maintain high standards for water quality is they have rather than a technology-based standard like filtration, they have a water quality-based standard. And if they fail those water quality-based standards, New York City is going to have to spend $16 billion to put in a water filtration plan. So they're quite concerned at present, but also what the future might look like, and they're really worried about these changes in magnitude and the timing of these flows as well. And the climate assessments that Jonathan was talking about, the GCMs, they've applied this to a whole series of watersheds in New York. Basically, it's pointing to earlier floods, a shift in the magnitude of floods, you're going to occur progressively early through the course of the year. So in conclusion, I'd just like to say that we have tremendous amounts of empirical evidence that has shown that certainly over the past 5 decades, we've had tremendous hydrologic changes occurring in New England. Again, all pointing in the same direction to increases in stream flow, primarily generated by increases in stream flow. And as Jonathan said, that world looks wetter into the future as well. So our summer precip, base flow, and storm flow are all increasing. The maximum size of the floods are occurring, are increasing, as well as the moderate size floods. We're getting less snow in New England than we used to. We're getting earlier ice out days, and we're significantly changing the timing of that spring freshet as well. All of this, I would say, is consistent with the climate models, also consistent with what we see then in terms of a warming planet. We can also look at this in terms of hurricanes and floods, and I'll just honestly say this, we can never, I think, associate a particular event to global climate change. And I don't think we're at that level of sophistication yet, but I would just say it's consistent with, again, what model projections are saying. And lastly, I would say our infrastructure is inadequate to deal with what these changing hydrologic conditions might be like in the future. Thank you.
Okay, we'd like to open up to questions, and I'm going to start while you guys are warming up with your thought processes. We're looking at the time changes that we've been looking at, the time frames. For example, the 1927-28 flood. Since then, there are an awful lot more people. Land use changes have been very prominent. And does that make us more vulnerable, socially vulnerable to these events than we would have been earlier?
The other side, of course, of vulnerability is mitigation adaptation. These are some of the things we always have to consider as well. Are we more vulnerable to it? Well, the boundary conditions are changing, I would say, in terms of what's going on hydrologically. Land use is a real touchy one. If you actually look at forest cover in New England, it's probably as forest covered now as it was 300, 400 years or so ago. But it doesn't mean it's the same species composition or community structure, but for parts of central Vermont and New Hampshire, it's probably as forested now as it was 300, 400 years or so ago. What we have is there's a greater concentration of population. I would say, and I didn't bring that slide with me, but if you actually look at population increases within the Connecticut River, basically it's a very uniform increase till you get down to about 40, 50 miles from the coast, and then population increases. We also see that with road crossings are fairly ubiquitous throughout the Connecticut River landscape. And so things like culvert and failing culverts, I would say that is ubiquitous throughout New England and not necessarily related to the population clusters, which are much more orchestrated spatially.
Have you seen statistics about these local flooding events and increased incidence of them? Having grown up here, I don't remember these being very common at all, except for the last 10 years. And they kind of moved down out of Vermont over into this region. And we've had them here in Hanover.
Blame it on Vermont?
We had one in 2005 right here in Hanover that took out East Wheelock and Reservoir Road. And, you know, our infrastructure never had to be designed for these flows. Those and Irene point out that you could have a babbling brook or not even have a brook. You may have a raging river when one of these events occurs.
Right. I would just say from a statistical standpoint, a lot of things are leaning in the direction of what you're talking about, a greater frequency of these microbursts. One of the problems, of course, with them is they're so concentrated spatially that they don't show up in a lot of the precipitation gauges that we have. But the one, the storm in August broke the record for intensity, amount of precip in a short amount of time for Lebanon. It broke whatever 100+ year record. And so, again, when I bet my reputation on what little I have on that, but there seems to be, anecdotally anyway, that there seems to be an increase in these microbursts. I would ask a question of Jonathan, I'll put him in the spot, is how well can models pick up on these sorts of localized phenomena? If we're there yet, or what's the, do you think we'd ever get to?
We're not there yet.
That's
Is the short answer. I think the other issue is that they're such rare events that it's tough to build up a long enough statistical record.
Well, they're not rare now.
Over a long, what'd you say?
They're not rare now.
Yeah, that's right. Exactly. It'd be interesting to look at the precipitation records and see if you can find something in those, you know, over 2 inches in an hour or something like that. Something can pop out of the record.
Eric, you had a question?
Yeah, I know, Frank, you do a lot of research on dams.
Right.
And given, from Jonathan, we got more precip coming. From you, we got more floods.
Hey, don't blame me.
I'm not blaming you. I'm saying, my question is, should we be doing more dams or flood control structures? And if not dams, what? What should we be doing to deal to mitigate more precip, more floods?
I would say the building more dams isn't necessarily the solution. And one of the ways it is that they're expensive, for one thing, economically as well as ecologically. And also, they may help at some scale, but not at other scales. And one I always sort of brings to attention here is I've done a lot of work on the West River in central Vermont. I don't know if people in Jamaica or Townsend, Vermont. The West River flows into Brattleboro. So the West River has 2 large flood control structures on it, built in 1961. So immediately downstream of those 2 flood control structures, you may have been spared of the flood. They stored upwards of 80. The reservoir was filled to about 80–90%. Immediately to the west, the Rock River comes in to the West River, and basically it peaked and it led to significant flood damages in Brattleboro. So do we want to start damming every river in Vermont and New Hampshire? I don't think that's necessarily the solution economically or ecologically. And I would say also up to Hurricane Irene, that land use impact has also greatly ameliorated some of these large floods. Again, there's so much revegetation occurring throughout parts of New England. I would rather see, I think, the non-structural solutions in terms of zoning might be a first course filter approach to deal with this before you start investing time, money, and ecological costs as well in some of these large structures. You can't build a dam everywhere, and we're not sure how effective they would be. The other thing, just to riff a little bit, is at a national scale, some work that Roger Pilkey has done in Colorado. We'd like to see the relationship, for every dollar we spend on flood control, what would you expect to be the changes in flood damages over time? If you're an economist. Going down, right? Instead, we see for every dollar we spend on flood control, it costs the nation anywhere between $5 and $8. Okay? So what happens is it breeds a false sense of security that there's no risk anymore, and we don't live in a risk-free world. And so basically, as you build the structures, if you build it, they will come. People move in closer. They want the river views, and when the floods do happen, because any dam could fail or could basically exceed its reservoir capacity, and basically you start spilling, and there could be a big flood associated with that.
Frank, the Hanover Conservancy is revising and updating its strategic conservation priorities with an eye to climate change and trying to confer some kind of resilience in the landscape. And what guidance would you have for us in terms of what land should we pursue and prioritize for conservation to protect downstream neighborhoods, say Reservoir Road or whatever?
Jonathan, why don't you take it? I would say, first and foremost, you should do an assessment of the culprits. Okay.
I called Peter Kawaki, and his answer, the Department of Public Works Director in Hanover, his assessment was, are publicly owned culverts, you checked them all, they're all fine. junk ones that we can't do anything about that are a hazard, then the town cannot take action on those. So that, I mean, that was the first place it went, but.
I would say also, probably in the areas that are most, going back to land use, the areas that have the greatest residential density, probably the ones that would be most vulnerable, because again, you're changing the infiltration capacity of the soil, and those culverts may not have been designed to handle that kind of change in impervious area. Maybe get a GIS map or something to look at impervious area. I'm sure you guys have something like that, access to that. So I would look what areas, where it's been, you think about if the problem is the culvert, and what's the age of the culvert, design of the culvert, and have the conditions adjacent to or upstream of that culvert, how dramatically have they changed since the time that culvert was constructed, might be a coarse filter way of going at it.
Well, then would you go after for conservation and protection, upland streams, headwater streams, wetlands that could be absorbed?
Right, wetlands, yes, definitely. Just the or off-stream retention ponds and things like that. So, one second, I think you had your hand up first.
Most of our building codes are based on, allowable areas are based on 100-year floodplains. And I'm just wondering what your educated guess is. My feeling is we should be taking our 100 or 500-year floodplains possibly and erasing the words 500 and writing 100 there. Do you have a feeling as to how many years of floodplain we should be thinking about in terms of new revised realistic building codes? Just based on projections through the end of the century?
I would say, maybe Jonathan can probably finish this up better than I can, but one of the things, of course, that's implicit within the definition of a 100-year floodplain is that you've identified the magnitude of the 100-year flood. Okay, and so the 100-year flood, and this is telling my students, there's one thing I want them to get out of my class when they leave, remember for the rest of their lives, and I have an audience, captive audience here, and I don't want to lose this opportunity. What is the 100-year flood? 1% what? 1% chance of occurring this year. Okay? If it occurs this year, what is its probability next year? 1%. Okay? So there's a misconception out there, I would say, in the public as well as in the planning world, that the 100-year flood is the time between floods of that size. It has absolutely nothing to do with the time frame. It's a probabilistic relationship. And so one of the things we're seeing is that the dice might be getting loaded now. And so what had originally been the 100-year flood magnitude was based on data that are probably incorrect now. There's probably something, what was probably the 200-year flood a few years ago might be the 100-year flood now. I don't know what the magic number is, for that. But again, I would say to revisit that in terms of what actually is it. And one of the things, without getting too heavy into statistics, oftentimes what's assumed in the statistical analysis is what's known as stationarity, that the mean and variance remain constant over time. And one of the things we're seeing, especially with these changes that are happening now in New England, the mean and variance is changing. Therefore, what your flood record is not truly representing the tails of the distribution anymore.
I think as a first hack approach, you could take the existing trend that you see in the precipitation record, which isn't going to be reflected in the 1 in 100-year storm, and just at least tack that on. Whatever, maybe you could do it as a percentage of increase. But I mean, getting out into the end of the century, it does get difficult with precipitation to predict. Like some of the best things that we can do is say, move away from the coast, because sea level is going to rise. If you live in a warm area, you're going to have more heat waves. So it's one of our, precipitation is one of our less robust predictions that we make. So it's tough, but at least, and planners especially can identify, I think, well, everybody can identify with historical trends, right? It's in the data. So that's one thing to always kind of hook your cart to.
I gave a talk right after Irene, and something the Upper Valley Land Trust assembled. He was one of the, someone I think from the Vermont Planning Commission. If you hear, I apologize, I can't remember your name. And he gave a great line. He said, he's doing the FEMA mapping, how FEMA mapping inaccurately captured what was going on with Irene. He said, you got to realize, if you live on a river called the Mad River or Roaring Brook, right? You might, they probably gave you that name for a reason. So you don't want to build your camp right next to Roaring Brook. So maybe that's the design. So I think Let's hear, and then.
Yeah, my question is really, many of the science is studying how people think, because it seems like the issue of reactive thinking and being circumstantially driven is what the driving way that people think. And what you project is really proactive thinking. This is what's going to happen. And to me, the issue is, how do you change what people think?
The short answer is we're trying, but it's really difficult. So I'm actually on a working group that's looking at human perception of climate change. That's funded by NSF, and we come together as a because I have no idea how people think or how basically how decisions are made. So we try to pull together the appropriate disciplines and all start talking the same language and see how we can best convey the knowledge to get some of those sort of proactive approaches. It wasn't in climate change, but there's a that's looking at how to use gaming, basically, because that becomes in a really effective way. I don't game, but it becomes in a really effective way to get your message across. It's been shown in a lot of scientific studies. So you have to have people like coming from technology and sociology and other directions to work with us as physical scientists to try to figure out what the best way to convey our message is and how to influence people, basically.
Because there's a financial issue there too. If you take Hanover culverts, let's just say, the natural reaction is going to cost us more money to actually put in new culverts that actually will meet the potential need here. So the reactive thinking comes into play managing your budget.
As I tell my students, what's the difference between a catastrophic flood and an extreme flood? An extreme flood is when your neighbor's house gets wiped out. A catastrophic flood is when your house gets wiped out. So to see this, if it becomes palpable, then I think people can become aware of it.
We've been talking about New England, but it seems to me we haven't been talking about the Southeast, Georgia and stuff. It seems to me that it's been the kind of period recently a lot of drought. So if the temperature, if our region is getting wetter and warmer, it sort of implies that the Southeast, for instance, would be getting
Drier and warmer.
Absolutely. And I'm just thinking from a long-term planning point of view, besides people wanting to move away from the coast, our region could be affected by an increase of population of people wanting to come this direction, which would put pressure on all that impermeable surface additions and things like that. It seems like those kinds of thoughts need to be implanted in people's planners' heads. Do you agree, or do you think I'm just like off the top of my head?
It's a good point. I don't know how people make their decisions about where to live, but certainly as water becomes more scarce in the Southeast or temperatures continue to drive up, you're going to have a migration that's going to go northward. I would expect.
It seems to me that after every even minor storm, the ditches on our dirt roads all wash out. And if you walk below the culverts and you have a ooze of sand and sediment, all the swimming holes get filled with sediment. What effect does that have on the ability of that channel to flood flows?
It probably can lead, this is a big loop here, but it could lead to increased flooding in the sense that if you're putting all the sediment into the channel from these small low headwater channels in the culverts, the bed of the channel begins to fill up. And so what had been the channel dimensions pre-deposition, now it becomes the channel tries to maintain some equilibrium shape and a gradient. Essentially now it's got too much sediment that it can handle, so it's got to change the bed elevation to mobilize that sediment. And so there is always a fear that more sediment coming into a system could lead to increased channel, but depends on the volume would have to start to accumulate over some period of time. But I think the other thing that maybe what you're hitting on as well is that, what's the expression, death by 10,000 whatever that is. And so it's all these like little things, that cost a nickel here, a dime there, and then the accumulation spatially and temporally leads to these progressive changes occurring on much larger scales, and the channels no longer have the capacity to handle that material. Question there, and then here.
Well, in the title, it was the discussion in relationship to agriculture, which we haven't really talked very much about, and understanding that it doesn't take a whole lot in an area which has a limited amount of high-quality farmland, such as New England, for the types of events that we've been having to take land out of production. I have 7 acres that's no longer productive because of Irene and the microburst this summer. There are half a dozen farms in Vermont that have lost much larger acreages than that that are no longer farmable. And so it's a very fine line. We don't need the data and all the accumulated knowledge is that there will be a very rapid effect, and it's a kind of an unknowable effect on agriculture. The Connecticut River Valley doesn't, in the river itself, does not get the type of flooding that some of the side streams and some of the smaller rivers get, and especially we were affected here, less so on this side of the river than the other, but for this year up in the Williston area, up in that area where they had such a saturation level that we produce, it doesn't take much for us to lose plant production. Degrees difference in temperature over a year can make land productive or not productive.
Yeah, well, I mean, to some extent, you're absolutely right. We didn't really touch on, I guess, agriculture at the margin. My question to you would be, why did you pull the acreage out of production? So what was the problem with it?
In Irene, it was under 3 feet of water, and in microburst this summer it was under 3 feet of water, which means I've lost, the production of 7 acres of land twice.
Right.
Is an economic cost to me in the tens of thousands of dollars, and which would prevent me from ever planting it again.
And I would say, so our work, I would say, my work takes a broader view and looks at much larger geographic areas. So I can certainly appreciate that those two events really put a dent in your production. But I would say that, no global climate models or
I understand that from a modeling standpoint, but my point of that is we have a very limited amount of agriculture here.
Yeah.
And that's the issue. That's probably
Most of it's floodplain.
Yeah,
It
it'd be
I mean,
interesting
that's
to
what
look at
Vermont
it.
is,
I was
floodplain.
thinking.
so maybe great land, and there's neither an economic or a legal way to make that usable under flood conditions.
Has the state offered to buy you out for that land, or?
There's no crop insurance. I received nothing whatsoever in those lawsuits.
So maybe instead of planting apples, you should plant citrus and bananas or something of that sort.
Vegetables, rice.
We could talk, one of the other things is, was it inundation or was it loss of land by tank erosion?
Primarily irrigations, but you can't harvest anything from that land.
Is there a question here?
My question is centered on agriculture as well. Some of our best land farming lands are located along rivers. So where do you see agriculture taking place 20, 30, 40 years from now?
It's a really difficult question.
What was it like?
So the question was, a lot of our good agricultural land sit on floodplains. Where do you see agriculture in 2050, mid-century? And I would say that's a good question, and I don't have a good answer for you. So because clearly you can't, if you just look at the climatological factors, you could try to race yourself up a hill or try to pull up into elevation. But that would be ignorant of what's already there. The land use is already there. So can we use that land, and does it have soils that will support agriculture? So I would say our work looked just basically specifically as kind of climatologically at how agriculture was able to survive. And beyond that, we haven't gotten to it yet.
Question there and then there.
speaking of sediment, one of the early shots you had was of the outflow at the mouth of the Connecticut River. Has there been a change in, let's say, the depth of the ocean there, or has there been any long-term issues from that huge outflow of sediment?
It's actually been muted because of dams. And so most of the sediment coming down the Connecticut gets stored in these reservoirs behind dams. So they had the largest suspended sediment concentration, the lower Connecticut is like 1,700 milligrams per liter or something like that, which is one of the highest ever. But it would have been progressively higher had not all that sediment been stored behind the tens of thousands of dams are within New England. So that's the stuff that sort of made it through. That's probably the stuff from this. I think a lot of that came down from central Massachusetts. And so the turbidity probably would have been higher down at the mouth. And basically what we see is one talk over beers, but any impacts of dams as well has led to a progressive amount of coastal erosion as well because all the sediment that gets trapped behind these reservoirs.
Well, I was just talking about the sediment that did actually arrive at the mouth. Has there been any measurement of that? Or
Not that I know of.
It's probably, I mean, it's obviously sediment, so it changed it somewhat, but I'm not sure. I doubt it's appreciable. Maybe the biggest impact would have been on water quality. Here I'm just a conjecture.
The question on agriculture brings to my mind the issue of the difference between accommodating climate change and trying to do something about climate change to reverse the process and bring us back to something that is not as traumatic.
Got any ideas?
Reduce carbon emissions. And how would you split the investment of the public investment between infrastructure changes to accommodate climate change and getting rid of carbon emissions?
Political answer, economic answer, but also just the whole, cap and trade, all these sorts of things. Now we've left my area of
big politics.
Yeah.
So this is one of the things that these IPCC reports are supposed to inform. These are supposed to go to policymakers, and I think the synthesis report is timed for. I'm not up to date on my UN framework on climate change when they all get together. They're getting together in Warsaw, I think, right now. But I think the synthesis report is timed to come out either right before or a little bit before the next big meeting, which is, does somebody know where the next, there's a big one where they hope to kind of shovel some actual action through. Because it's a global problem. I mean, you can mitigate on the regional scale, but...
So what I might suggest, if you have more questions, come on down and pigeonhole these two guys and see if we can get more information out of it. And in the process, grab some more food and keep asking. Let's keep coming questions going. Thanks again.